everyone. Welcome again. So today we'll be doing the module Chemical Monitoring and Management with a focus on the coordinate covalent bond. And in this particular lesson, we'll be talking about oxygen allotropes and their properties. So the first thing is, what is an allotrope? So an allotrope is any element that can exist in multiple forms of the same state. So if you think of carbon, carbon has the form of diamond, which is a precious gem, also in the form of black carbon or soot, coal, or graphite, as well as the Buckminster fullerenes as well. So generally, all allotropes are elements that exist in the same state, but of a different form. The key difference, though, is how they're structured. So with graphite, we have planes of hexagonal carbon rings, whereas diamond is a network structure of covalent network bonds. So another example is elemental oxygen, and it exists in a number of allotropes, and we'll concentrate on the main three, which is the oxygen radical, the ozone molecule, and the diatomic oxygen molecule. So in gaseous state, oxygen has three forms, as I just mentioned. So there's the oxygen radical, which is just O, which is a single oxygen atom. There's the oxygen molecule, or diatomic oxygen, which is the oxygen that we're all familiar with and is what we breathe in and out. And lastly, the ozone molecule, which is O3, which is here, or triatomic oxygen, which is the gas that protects us from ultraviolet light and as well as does other things for us as humans. So the oxygen radical is a single oxygen atom, as demonstrated by this pink ball here. And it has 6 electrons in its valence shell and 2 unpaired electrons. So because it's a single atom and it has unpaired electrons, it's very reactive and incredibly unstable. And in our atmosphere, they only exist for a short time because of that instability and also their reactivity. Because of the high intensity radiation that strikes our atmosphere, they only exist in the highest areas of our atmosphere, so greater than 15 kilometers. So a reaction that generates these oxygen radicals, with the dot representing the radical, is oxygen gas plus this UV light from the sun converts that oxygen gas into 2 oxygen radicals. Diatomic oxygen, however, is the oxygen that exists on ground level and is what we breathe in. And it's 2 oxygen atoms bonded together, as you can see here, and is necessary for respiration. So in previous lessons, we talked about what respiration and photosynthesis was. And so this is the gas that's key to that process. So some properties of diatomic oxygen is that it's odorless. So if you breathe in oxygen, you're not likely to smell it. It's colorless. You don't see any color when we walk around and breathe the oxygen in the air. It's stable. As you can see, it exists fairly continuously throughout our existence. As we walk around, it doesn't break down. And it's non-polar. So remember that polarity is based on how electronegative each component is. And because you have 2 oxygen atoms, they're equally electronegative. So it means that you have a non-polar substance. And it's highly reactive. So for instance, if you leave out some metal in some air, it will oxidize and convert into, say, rust or corrosion. So it reacts quite strongly with many things in our environment. So what we use oxygen for is obviously sustaining life. As I mentioned, respiration is key. It's a process that we need to accomplish in order to survive. It's where we get our energy from. Higher concentrations of oxygen are used for patients with breathing difficulties, or they can't absorb oxygen from the air as effectively as healthy humans. And also combustion of fuel. So when we burn fuel for our transport or for creating electricity, we need to consume oxygen because that's how we release that energy that's bound within those chemical fuels and those kind of things. We also use it as an oxidizing agent. So when we have particular metals or particular substances that we want to produce, but we have the pure metal form, we can use oxygen to react with it so that we can get something that is industrially useful. So for instance, magnesium oxide, which is a strong ceramic substance, we basically burn magnesium with oxygen gas to form magnesium oxide. Similarly, if we want to produce sulfuric acid, we can mix sulfur, pure sulfur, with oxygen to form SO2, dissolve that in water, and we'll get sulfuric acid. So also mainly used in the industrial manufacture of iron, steel, and also sulfuric acid, as I mentioned. The last allotrope that we'll talk about is the ozone molecule. So this is triatomic oxygen, so you get 3. And it's drawn in this way because it is actually a bent structure, but we'll cover that in a second. So it's poisonous and a powerful oxidant. So ozone is much more potent as a reactant than oxygen gas or diatomic oxygen, and so it's much more dangerous to us as humans. In our troposphere, so remember from previous lessons, troposphere is the bottommost layer of the atmosphere, closest to the ground, we have only very low concentrations of ozone. And it readily breaks down or dissociates into oxygen gas and oxygen atom, so the oxygen radical. The properties of ozone are a sharp irritating electric odor. So for those who catch the train, when it starts to slow down, you get this really strong sort of fuzzy smell, and that's ozone from coming from the breakdown of oxygen gas because of that electricity. It's a pale blue. So the reason why our sky is blue is partially because of the ozone present. It gives that blue color. Like I mentioned, it's unstable, so it decomposes to form oxygen gas or diatomic oxygen. It's polar, so because it's bent like this, it provides some polarity rather than being a straight chain molecule like oxygen gas. So it has some polarity, not as much as, say, water, but it's still a little bit. It's extremely reactive, as I mentioned. It's much more reactive than oxygen gas, and it's poisonous. So greater than 20 parts per million will give you a poisonous effect. So what do we use it for? Because it's poisonous, like I mentioned, we use it for sterilization purposes. So water supplies and swimming pools can be sterilized with ozone. Likewise, in our bodies, we use it to remove pathogens or germs, viruses from our body. It's used as also to sterilize stagnant air in, say, abattoirs or slaughterhouses and in underground railways. Now, some chemical properties of ozone. So what makes it different from oxygen gas is that it's very highly reactive and will oxidize nearly everything, with the exception of course, gold and platinum. So here's a simple reaction. Zinc plus ozone gives you zinc oxide plus the oxygen gas. It also attacks double bonds, so alkenes from production of materials, you should remember, are used to manufacture plastics. So by breaking down those double bonds, we can deteriorate textiles and rubber. So a way to distinguish between oxygen and ozone are the following. So you have a glowing splint test. So when we put a glowing splint, so something that we've lit on fire, that we've blown it out, if we put it in pure oxygen, it'll combust again and it'll burst into flames. Whereas to see ozone, to know if it's ozone or not, there's a characteristic odor, though I don't recommend smelling it, but there is that odor, or you could use infrared spectrometry. So we've covered in this lesson oxygen allotropes, and what an allotrope is, and what the 3 main allotropes of oxygen are, and their properties. So if that's okay, we'll move on to some questions to reinforce all the things that we've learned in this lesson. So question 1, which of the following options correctly describes molecules of oxygen gas? So we have hydrogen bonds are present, highly reactive for oxygen, and for ozone, highly reactive pungent molecules. So this side is true, but however, the whole question is wrong. B is wrong because there's no hydrogen bonds in oxygen gas. So C, also incorrect. Diatomic with polar linear molecules, which is true, and molecules contain 3 atoms, which is also true, but again, this is not fully correct. It doesn't, because this is not polar. Oxygen is not polar. So D, again, is not correct. Double covalent molecules with a bent shape, covalent molecules with ionic bonds and a linear shape. So oxygen is not bent, it's straight. However, covalent molecules with ionic bonds is also incorrect, and it's not linear. So that leaves A, which is correct. So it's diatomic with non-polar linear molecules. So that's true. We've talked about that. There's no polarity in oxygen gas because they're both equally electronegative. And ozone is bent and it's slightly polar because of that shape. So moving on to question 2. Which has stronger intermolecular bonding, ozone or oxygen gas? And explain. So ozone to ozone is a polar molecule because the shape of ozone is bent. So that bent structure gives you slight polarity, which therefore has dipole-dipole forces because of that polarity, and it also has dispersion forces. Now, because oxygen is nonpolar, it's linear and symmetrical, it only has dispersion forces. So that means that the ozone to ozone bond is much stronger than the oxygen to oxygen bond, because that polarity and that dipole-dipole bond increases the strength of the intermolecular forces. So question 3. Define the term allotrope and identify an example. So remember that allotrope is any element that can exist in multiple forms of the same state, but are different in the way they're structured. So different forms of an element in which the atoms are arranged differently, so the forms have different properties. So remember that each allotrope has different properties to one another, simply because their structure is different. So an example would be carbon, also oxygen you could have used from all the stuff that we've talked about. But in this case, carbon. So we have graphite, which is the stuff in your pencils, diamond, of course, which is in rings and various other jewelry, and fullerenes, which are almost soccer ball looking type molecules. Now, if that's okay, we'll move to question 4, which is justify the classification of O2 and O3 as allotropes. So if we look here, the verb is justify. So remember that when we talk about HSC and answer questions, we have to think about what the verb is telling us. And so in this case, justify, remember, just think back to how you would answer this question. So firstly, both substances are composed of oxygen atoms. So there's nothing else in these molecules except oxygen. But they're arranged very differently. So oxygen has single linear double bond, and ozone is that bent triatomic oxygen form. Like I said, oxygen is diatomic with 2 atoms joined by double covalent bonds. Again, yes. And ozone molecules have 3 oxygen atoms, 2 of them joined by double covalent bonds and 1 joined by the coordinate covalent bond. So we'll talk about exactly what a coordinate covalent bond is in future lessons, but for now, just this is what the difference is, and so we can call them allotropes because they're essentially the same element, just bonded differently to one another. So just remember, whenever we're answering questions, think about what the verb is asking us to do, and then you'll have no problem with any HSC question. So question 5. So define free radical. So again, define is a very simple verb, and so we can work it out easily. So we just have to say what the meaning of free radical is. So a reactive particle that contains 1 or more unpaired electron in its outer shell. So the oxygen atom is a free radical because it has 2 unbonded electrons in its outer shell. Like I said, oxygen, there are others, of course, chlorine as well, and various other ones. Chlorine, which affects the ozone layer, and several others, which we could talk about. But in this case, oxygen is a free radical containing 2 unpaired electrons in its valence shell. So this concludes our lesson for today. Now, we covered what an oxygen allotrope is, the three main oxygen allotropes, and what their properties are. So next week, I think we will talk about the coordinate covalent bond and how it affects the structure of oxygen. So I look forward to seeing you in the next lesson.